In this section, we're going to be exploring an extremely important quantity that we can measure for any n by n matrix, namely the determinant of that matrix. We're going to begin by motivating this concept of the determinant by looking at the quantity for 2 by 2 matrices and kind of exploring a geometric interpretation of the determinant. So we did introduce this idea in a previous section when we were talking about invertibility. So to remind you, for a 2 by 2 matrix in particular, of the form ABCD, the determinant of A is given by the quantity AD minus BC. And what we're going to see in this video is that the determinant measures how a matrix transformation changes area. So to begin, we want to remind you of a formula for the area of a parallelogram. If we've got a parallelogram like this, where we are looking at base and height, B and H, then area just equals base times height. So we're going to be using this in the next few slides here. So let's take a look at the matrix 3, 0, 0, 2. And what we want to do is think about this as a matrix transformation and kind of recall the geometry of a matrix transformation. So just as a reminder, when we're thinking about this matrix as a matrix transformation, we think of this first column, 3, 0, as kind of the transformed vector of the vector E1, which is just the vector 1, 0. So we go from 1, 0 to 3, 0. So we basically take 1, 0 here, and it stretches out to 3, 0. So for this particular matrix transformation, we kind of have in the horizontal direction a scaling factor by 3. Similarly, this second column here, 0, 2, is going to be the transformed version of E2, which is 0, 1. So 0, 1 goes to 0, 2. So we take 0, 1, right, and kind of stretch it by 2. So this matrix as a whole, A, is going to stretch the horizontal direction by 3, or scale the horizontal direction by 3, and scale the vertical direction by 2. So, sort of combining those things, we're scaling all of space by 3 times 2, or 6. And so a couple of things to look at here. If we take this image here, so what this image shows is the transformed version of the unit square. So the unit square is going to just be, the square where we take as two of the sides E1 and E2 and, kind of draw the square with those as two of the sides. So we have our X and Y axes here. So the unit square is just going to be this one here. Right, so if we were to transform this unit square under this matrix transformation given by A, then we'd end up with this rectangle over here. Now, if we compute the area of, first of all, the unit square has area just 1 times 1, base times height, or 1, and the area of this rectangle after the transformation is going to be base times height, which is 3 times 2, which is 6. Now, if we take the formula we saw a second ago for the determinant of a matrix, AD minus BC, and apply that to this matrix here, the determinant of A, we would get 3 times 2 minus 0 times 0, AD minus BC, which is 6. So you can see that, at least in this case, and we're going to see kind of more examples to hopefully convince you that this is true in general, that the determinant of a matrix, at least for a 2 by 2 matrix, can be interpreted as, in some ways, the kind of, area of the unit square, how much the area of the unit square gets scaled under the transformation of this matrix. So let's take a look at another example here. A now is 1, 1, 0, 1. So again, E1 is going to get transformed just to itself, so it doesn't change. So there's no sort of horizontal change in this case. But E2 goes to 1, 1. And so you could see that, this transformed unit square has sides now given by the transformed version of E1, which is still just E1, and the transformed version of E2, which is now going to be the vector 1, 1. And what we end up with is a parallelogram here. Now, if we were to compute the area of this parallelogram, we would do our base times height. The height here is 1. The base here is 1. So the area of this parallelogram is going to be base times height, which is 1 times 1, which is just 1. If we take the determinant of the matrix A, we'd get 1 times 1 minus 0 times 1, AD minus BC, which is just 1. So you could see that, again, the determinant of that matrix tells us, the fact that we really aren't scaling the unit square in this case by any factors. We still just get 1. So that isn't to say this transformation doesn't do anything. We can actually see, it sort of is going to skew things a bit, but it doesn't change the area of any object. Let's look at this example, 3202. So playing the same game again, our E1 goes to 3, 0. So we're sort of scaling horizontally by 3. E2 goes to 2, 2. And so we could see there is going to be a scaling factor here. If we take the area of this resulting parallelogram after transforming the unit square, we have height 2, base 3. So the area of this is going to be 3 times 2, which is 6. The determinant of this matrix A is going to be 3 times 2 minus 0 times 2, which again, of course, is 6. So this tells us that any object that we look at, if we were to transform it in under this matrix transformation, then the resulting object would have area 6 times the area of the original object. Again, there may be other things that are happening. It's not simply just going to scale the area. It might move things around a little bit. As we can see, our unit square became a parallelogram. It didn't just sort of scale and become a rectangle. But, in terms of the area, it scales by that determinant. Okay, here we have another example. So this particular example shows that we have some rotation happening now. So again, 1, 0 goes to negative 1, 1, and 0, 1 goes to 1, negative 1. So we have sort of some rotation going on, and then there's also some scaling. How much do we scale by? If we were to compute the area of this object here, this ends up to be sort of a rotated version of a square. And so you could, compute the side lengths of this square using the Pythagorean theorem, or you could kind of just, rotate your head a little bit and think of these different triangles. These little quarter triangles would each have area equal to exactly half the area of kind of this unit square here. So these would each have area 0.5. So 0.5 times 4 is going to equal 2. So the area of this equals 2. And again, you could have figured out the side lengths by the Pythagorean theorem would be root 2. So root 2 times root 2 would be 2. So another way to do that. And then if we look at the determinant of A, we would get negative 1 times negative 1 minus 1 times negative 1. So that's going to be 1 plus 1, which is 2. So in this example, we have sort of the area getting scaled by 2. So, everything would double in size. But, we also have sort of some rotation going on. So the determinant is useful in telling you some information about this transformation, namely sort of how much it's scaling, but doesn't give you all the information necessarily. Another example here. So 1, 0 goes to 0.5, negative 0.5. So this vector here, 0, 1 goes to 0.5, 0.5. So similar to the last one, we have some scaling as well as some, rotation. And if we were to figure out the area of this particular example, again, we could do this a few ways, but probably the easiest I can think of is, recognizing that each of these little quarter triangles is exactly half of one of these squares. these squares have side lengths 0.5 and 0.5. So, those would each be 0.25. So each of these quarters would be half of that. If you multiply that by 4, you would end up, getting the fact that this whole thing would have area equal to, I guess, that point, point two, 0.125 times 4, so zero point 0.5, okay? And if we were to find the determinant of this matrix up here, that would be 0.5 times 0.5 minus 0.5 times negative 0.5, so that's 0.25, minus negative 0.5, so plus 0.25, so that's 0.5. So again, matching up. And one more example here. So in this case, we have 1, 0 goes to 4, 2. So 4, 2. And kind of along this, right? And 0, 1 goes to 1, 2. So these land sort of on each other. We've collapsed that unit square just onto this line here, and we don't end up with sort of a two-dimensional object as well. We just end up with a line. The area of this would just equal 0. And if we figure out the determinant of A, we'd get 4 times 1 minus 2 times 2, which would be 4 minus 4, or 0. So we see that the determinant being equal to 0 tells us that we're going to end up with, in 2 dimensions at least, this sort of collapsing either onto a line, or I guess in the worst case onto just the point 0, 0 under these matrix transformations. One thing I want to point out here is that the columns of this matrix are scalar multiples of each other. So what we could see is that they are not linearly independent. So they're linearly dependent columns. And we know from our earlier study that tells us that this particular matrix is not invertible. So it has a determinant equal to 0, but we can see sort of how that plays out geometrically with this matrix transformation of the unit square example, and also this area example. So hopefully kind of connecting some of those dots. What we're going to see in future videos is what this might look like a little bit more generally for both 2x2, 3x3, and maybe even bigger matrices. There is a 3x3 geometric interpretation. As we get larger than that, it becomes a little bit trickier to visualize the geometry of things in 4 or 5 or higher dimensions, but theoretically, at least, you can kind of think about these concepts, and kind of exploring a little bit more why this AD minus BC thing does indeed give you that area in general. We only did a few examples here to give some motivation and set things up a little bit, but kind of the general idea that the determinant, this AD minus BC quantity, does in fact give us the area, or the scaling of the area, I should say, is something we want to look at a little bit more in future videos.